And I'm actually going to just do a short video. Yeah, we've calculated PQ, magnitude of PQ, QR, magnitude of QR, and then we calculated RS and SP with the aid of a couple of pictures just to clarify what these things mean on the basic shape. Then we did the dot product of RS, I think PQ with QR, just using the methods on the board, that the video that I asked you to view the other day, where we define the dot product, and we do PQ dot QR using the dot product and using the distributive law. And then we note that we can write PQ in terms of the I, J, and K components using the 0I, QR we're using the 0J. And we see that the components of this vector PQ could be expressed as 0, 5, 2, and QR as negative 5, 0, negative 4. And then that the dot product turns out to just be 0 times negative 5 plus 5 times 0 plus 2 times negative 4, or negative 8. Having calculated that, we go to the usual definition of the dot product. Now, this definition implies all this, and these imply this definition. This is an analytical definition. This is a geometric definition. Okay? So, you've seen this when you saw the previous video. So we simply apply this to find the angle between PQ and QR. Okay, we have the dot product, it's negative 8. Well, that's this side of this equality. On the other side, we have magnitude of PQ, magnitude of QR, and the cosine of theta, so that magnitude of PQ, magnitude of QR, cosine theta is negative 8. We then solve for theta. Okay, the cosine of theta, well, we write the numbers for magnitude of PQ, magnitude of QR, times the cosine of theta equals the dot product that we easily calculated, or a little less easily. This is the way you're usually going to do it, but you need to see this. And then cosine of theta is negative, well, and then we solve. Divide both sides by square root of 29, square root of 41, we get cosine theta. So theta is the inverse cosine of this quantity, which I didn't have room to write in the parentheses. Okay, doing that, I did some estimates in my head that I might detail in another video. And I estimated the angle to be 103 degrees. Now you can go ahead and calculate it using your calculator and have a lot of amusement if I missed it by much. I don't think I missed it by too much, but I might have. Okay, then we calculate RS cross SP using the definitions in the board that I just showed you when it included the cross products of all the I's, J's, and K's with one another. So we have this cross product. We use the distributive law just the same way we did on that video. Discussed it in more detail in the class. And we got all this. And maybe it's accurate, maybe it is, and I made a few errors when I did this. And I think I corrected them all, but maybe not. And ultimately then we find that the cross product is 25I plus 32J plus 20K. You usually won't calculate cross products with the distributive law unless I ask you to do it. Okay? You usually use the determinant definition, which you can understand by reading it, assuming you know how to do determinants, and that's part of your prerequisite courses. So I have to assume you do. If you don't, let me know. I'm actually creating kind of a remedial site where you can go to pick up things that maybe you didn't pick up in your original courses. And I can pretty easily get one on determinants. I haven't done that, but I think I can very easily. Okay, set it up in 30 minutes or something, and I'm glad to do that. Unit vector then, okay, well, we have our cross product. Now, the cross product inherits the fact that the cross products of the I, j, and k vectors with one another are always perpendicular to the two vectors. Now, if the two vectors are parallel, you can't get a vector perpendicular to both. That's why I dot cross I, j cross j, k cross k are 0. In any case, we then demonstrate the right-hand rule. For example, calculating negative 20 j cross I, put our fingers in the direction of j, turn our hands so that when we curl our fingers, they point toward I, and we see that the thumb is in the direction of negative k. So j cross I is negative k. You don't always have to refer to the list. It's totally consistent with the right-hand rule. Okay, so having gotten this vector, this cross product inherits the properties of the I, j, and k vectors and their cross products. What in the world just fell? Gives you a vector perpendicular to both RS and SP. Okay, so we have RS, we have SP. A vector perpendicular to these is perpendicular to the plane defined by RS and SP. We want to indicate that direction perpendicular to RS and SP by a vector that we can actually draw on our figure, a unit vector. So we get a unit vector in the direction of this vector, and that unit vector is just going to be the vector divided by its magnitude. When you divide a vector by how long it is, you get a vector of length 1, but it has the same direction as the original vector, and that's just a basic property of multiplication and division of a vector by a number. Well, we do this. It's a very simple calculation. The magnitude is just the sum of the squares, square root of the sum of the squares of the components. And then I estimated this, and estimating just to one significant figure, I got a vector that's not quite a unit vector. I think its magnitude, if you work it out, is about 1.08. Okay? But that's because the 0.6 and 0.8 are a little high, although I think what you get might round off to 0.6 and 0.8. 0.4 may be a little low. If you do it with complete accuracy, of course, you're not going to be able to express it as a decimal number, but the more significant figures you figure this out to, the closer your sum of the squares of magnitudes is going to be to 1, so that its square root will be close to 1. Okay, so anyhow, here's the unit vector, here's the unit vector, and this unit vector is perpendicular to the plane of PR, of the vector RS and SP, and this is a big deal.